Hello, I'm Lee Harrison from Siemens EDA. In this session, I plan to look at how we are all having to adapt to the rapidly evolving automotive IC industry, and how together with ARM, Siemens EDA have gone some way to creating a standard reference architecture for the automotive safety island, and how this can be used to really enhance the test and safety capabilities of your automotive IC, and where it can be extended to really enhance the capabilities of your overall system. Then, with these additional capabilities, what can we do with all of the data that's created, and how do we manage this in a secure manner? I'm sure you've all seen how things have shifted in this automotive IC segment. You've all seen the predictions that by 2030 the cost breakdown of any new vehicle will have changed significantly, with the predicted 50% of the cost now being in the electronic systems of the vehicle alone. So what does this mean in reality? There's been a big shift from where electronics have been used in vehicles in the past, and we are now seeing a massive increase in the amount of compute power that's being added to vehicle systems today. The use of this compute power is very varied and can be used to manage everything from advanced infotainment systems right the way through to the latest ADAS. Obviously, with the ultimate goal being autonomous driving. All this results in a massive shift in the design and architecture of our vehicles' electronic systems. And then, of course, we have safety. I'm sure you're all well aware of the ISO26262 standard and the increasing number of other regulations that are now governing the electronic systems within vehicles. With the increasing complexity of automotive systems, the implementation of safety has also become a lot more complex. And the ability to make sure all of the devices are well covered from a safety perspective has become obviously a far more of a challenge. So the use of safety analysis and safety insertion EDA tools has become a lot more prevalent within the industry, especially with these new design styles. And with all of the technology we now add into the device for both test safety and even functional monitoring, we're able to produce a huge amount of data on the overall health of the device when it's in operation. To a number of organizations in the automotive ecosystem, this data is extremely valuable. I'm sure many of you would have heard the term that data has become the new oil in the automotive industry. The big question is, how do we safely extract that data, make sure it's secure and accurate, and then how do we use that data efficiently? But first, let's just take a look at how the EDA technologies have advanced to take care of all of the requirements for safety, security, and even beyond. On an automotive IC, we have a number of different technologies that we can add. Starting with the more traditional functional test technologies such as memory-based and logic-based, we are able to detect physical defects on the device. We then have functional safety, where we can add a number of functional safety mechanisms into the device which take care of monitoring other anomalies that occur during the functional operation. And then we have embedded analytics, where we can add monitoring IP that are able to check performance, safety, and security of the function of the device whilst it's in operation. By bringing all of these technologies together, we're able to really enhance the safety and security capabilities of any automotive device. A good place to start when we look at the overall architecture that's required to manage this in-system content is that of the test structures. If we look at these in-system test structures, as I said before, we have both logic-based and memory-based. And these in turn are connected to an in-system test controller. In the case of Siemens EDA, we use IEEE 1687 as the overall architecture to manage and control our test instruments. So it's the in-system test controller that manages these IEEE 1687 IJTAG transactions. But even with the in-system test controller in place, we still have the requirement to be able to run the test instruments in a number of different configurations. And here are just 3 common examples of how we see in-system test controller being used in different scenarios. To start with, we have key on or power on test. With this, especially in the automotive space, the requirement is for a very short test time. If you can imagine, these tests are being run at the startup of a vehicle. So the requirement there is to get the vehicle ready for operation as quickly as possible. So here we tend to run as many tests as we can in parallel, and we may also run a basic level test just to ensure the device is operationally correct. But we need to do this and also meet the aggressive test time requirements. Then we have key off test. Here we effectively have an unlimited amount of time to run the tests. So typically with a key off test, you tend to see a more thorough, more detailed set of tests being run. So for example, with memory BIST, you may see a more detailed algorithm being run. In logic test, you may see an extensive set of patterns being run to reach that extremely high additional test coverage. And then we have online tests, which is probably the hardest scenario to manage, because the requirement here is to enable the test to be run whilst the device is in its functional operation. And certainly for the BIST test, the requirement is to take whatever part of the design is being tested offline for the duration of that test. And also typically the BIST tests are destructive. So all of the data that's in that part of the device will be lost and reset back to a known state. However, with the complexity of these devices increasing and the quality standards and requirements, especially with safety critical applications, running online tests is now becoming a requirement. So we can now see how our test instruments can be run from an in-system test controller and how we can have different configurations for each of those test instruments. Now let's take a look at how the in-system test controller is managed itself to enable it to run and collect the data from the tests at the required times. In this diagram, you can see a more detailed representation of our test architecture, which includes our test instruments, logic BIST and memory BIST, connected up through the segmentation bits to our top-level tap controller. You can see how the in-system test controller is driving that tap controller to manage all of the test infrastructure on chip. So let's take a look at what actually manages the in-system test controller itself. You can see there's 2 types of control mechanism. One is a very basic DMA interface, which can enable certain tests to be run just by the control of a few pins. And then we have the CPU interface. And it's this interface that we're really interested in, because we then hook that up to a CPU, and then you can create an overall safety island architecture. Now let's take a look at the safety island architecture implementation in a little bit more detail. On the right hand side of this diagram, you'll see a typical automotive device with a mixture of our test instruments embedded. So memory BIST and logic BIST. And then the IEEE 1687 test architecture. On the left hand side, you will see the safety island area itself. And the first thing you'll notice is we've isolated that area from the rest of the device. This is something that's not essential on all devices, but certainly when you're targeting the ASIL D level, which is the safety critical type devices, this may be a requirement. However, it's always good practice to make sure that the safety content within a device and its management is separated from the core function of the actual device itself. So within that safety island, you can see a number of different test components. Firstly, we have the tap controller, which is the overall driving component of the IJTAG network. You have the mission mode controller, which is the in-system test controller. And then, as we discussed, in the way in which we can drive the in-system test controller is through a safety manager CPU. And in this case, we've chosen the ARM Cortex R52, which is an automotive grade CPU, and is really designed for this type of task. So to interface the in-system test controller with the ARM CPU, we add an additional piece of IP, which is the ARM STC controller. This self-test controller interface really bridges the communication gap between the ARM CPU and the Tessent mission mode in-system test controller. The software within the safety manager CPU really then controls and defines which of those test scenarios that we talked about earlier get run and at which particular time. So really detailing when we can run a key on test or when it's safe to run a key off test. And also with regards to the online testing, which is obviously running during the functional operation of the device, the safety manager can really decide when it's safe to take part of the device offline and run that online testing. Obviously, this architecture is not set in stone, and many designs will require a slightly different configuration. But as a starting point, the reference architecture that we have here gives you a really good introduction on how to build this type of system and to get you started with the safety manager on your automotive IC. In this slide, you can see some really basic bare metal code that was written on the example reference architecture. Here you can see parts of C code which specifically reads and writes to areas of the mission mode controller to trigger the running of the various BIS tests. Once the BIS tests are complete, we're able to read the results of those tests back into the safety manager. So, on a full automotive device, you can simply control all of the test content within the device via your safety manager CPU. And it can be done dynamically, controlled through the software that's running on that CPU. So any enhancements or changes to the way you need to run those tests and the frequency and even the order in which you run those tests can be updated once the device is in the field by means of a simple update to the safety manager software. So in the reference architecture, I talked about just straightforward test instruments. However, once you have the safety island implementation done, it's very easy to extend this into other technologies that you can embed in your device to help with the collection of health and reliability data. For example, the connection to the safety island could be extended to things like the functional safety IP, to monitor the various flags that get raised from that functional safety IP. You could also connect it up to the test and embedded analytics IP, which will be running in functional mode, collecting performance, safety and security data based on the functional content of your design. Also, if you embed various parametric monitors into the device, we are also able to collect the data from those as well using the safety island application. So what do we do with all the data once it's collected? Obviously, if there's any immediate action that's needed, for example, if any flags get raised from the functional safety IP, we can have the software instruct the system that there's an issue with a particular part of the device. The same occurs from the test content. If we run any of the structural tests and we detect a defect, again we can raise that immediately to the overall system controller. For the bulk of the data, for which we need to take no action at all, it's possible to make the connection to an external interface. There we can extract the data whenever possible to a cloud-based service, where we can then do deeper analysis on the data alongside similar data collected from a whole number of vehicles out there in the field. That gave quite an abstracted and high-level view of what a typical system would look like. Now let's dive into a more detailed view. And we can talk about some of the different technologies that we pull together to build a whole automotive system. First of all, we've got functional safety. Here you can see on this block diagram of a typical device, we have a number of different functional safety mechanisms. We've got logic such as parity, logic duplication, ECC for memories, and even embedded analytics and test structures such as memory BIST and logic BIST, all of which can be used as functional safety mechanisms and monitored whilst the device is in functional mode. Then we have the manufacturing tests. In this example, some of the functional safety structures can be used for both safety mechanisms and manufacturing tests as well, again such as logic BIST and memory BIST. But in addition, we also have compressed ATPG. This gives the additional high quality coverage and quality that the device needs when in manufacturing. All of this test technology, both the BIST and the manufacturing test, sits on an industry standard architecture, the IEEE 1687 IJTAG. This is then hooked back to the industry standard tap controller with the regular tap interface that goes to external pins. However, internally, the interface can also be intercepted by the in-system test controller, the mission mode IP. The mission mode controller intercepts the tap pins and is able to deliver the test sequencing information and test setup information required for those tests when running in system mode. The way that those test sequences are delivered, as we previously discussed, is either via a very simple DMA controller or via a CPU. That CPU can provide dynamic information in terms of test configuration and test scenarios, almost on the fly. So as the system is running in its functional mode, the software running on the Safety Manager CPU can determine which tests need to be run in which timeframes. And it's not all just about test delivery. We can also collect the results back via the IJTAG network, through the tap controller, into the mission mode controller, and back up to the Safety Manager CPU. So the Safety Manager CPU can really manage all of the test content and control it, and also look after the results. And then, based on those results, it can make decisions on what the vehicle and the other systems in the vehicle need to know. The additional parts of all this is the embedded analytics infrastructure. This can sit alongside the test infrastructure, but due to some of the interface requirements on the embedded analytics IP, which require a higher bandwidth data communication than the regular IJTAG, we can connect the embedded analytics architecture directly into the Safety Manager CPU via industry standard bus such as an AXI or APB. When we pull all of this technology together, you can see we add a wealth of additional safety and security technology to any automotive IC. And through the Safety Island architecture and the Safety Manager CPU, we've got a central point where we can control all of that and we can manage it. Having a central point where all of the data comes back to gives us a better chance of understanding exactly what's going on the device. So we've talked about the different types of data that can be generated on chip and how we can manage that with the Safety Island and the Safety Manager CPU. Typically, with this structure, we are making reactive decisions and making those reactive decisions based on individual occurrences within that particular device. However, if we're able to collect the data from that device alongside the same data from millions of other devices all running the same software in the field, we can provide a wealth of data to do additional layers of analysis. So by pulling all of that wealth of data together, we can really start to build up an accurate profile on top of the performance of the device. Also the reliability of the device and how it ages over time. That provides the automotive manufacturers with information they need to make proactive decisions on maintenance, updates, and all of those type of activities. And with the wealth of data that we're collecting in the field, we can also link it back to the design and manufacture data that we collect during the initial concept and design phases. Add that to the data that we collect when the device is manufactured, and this enables the auto manufacturers to really look at the trends and the future and how they can improve the reliability and safety of the devices for future vehicles. So I hope that's given you a real good introduction to the safety element concept and the technologies that are linked and controlled by the overall architecture. If you have any questions about this session today or the technologies that have been covered in this short overview, please feel free to reach out directly and we can have a discussion about how we can help you achieve the safety and security requirements of your automotive designs. I hope you enjoy the rest of Dev Summit, and I look forward to seeing you all hopefully in person in a future edition.